on the agenda topic, as I mentioned, Mr. Israel Stein will talk about in a minute or so on FibroLAN introduction. Then, Mr. Shamir Stein, who is the CEO, will walk us through covering the entire agenda for today's webinar. So he's going to start with the architecture and key characteristics of backhaul and fronthaul, both in LTE and 5G networks. Next would be 5G RAN evolution and Oran reference architecture. He will then talk about different Oran topology and typical deployment scenario with the emphasis on timing. And in the end, he will introduce a few key products from FibroLAN that will address different Oran topology and development scheme. So this session is going to be for approximately 1 hour. We will try to finish the presentation part in 45 minutes or so. So we'll keep last 10-15 minutes for question and answer session. You have question and answer tab below your screen. And whenever you have any questions, please put your question in the tab, and we'll address. We'll take it up towards the end after we finish our presentation. Thank you again for your time, and I hope this webinar would give some interesting insights, and we look forward to meet you guys as and when opportunity allow us. Over to you, Israel.
Okay. Let me start. Good morning to all. My name is Israel Stein. I am in charge of business and business development. So I hope that after all this COVID situation is over, I will have a chance to meet some of you in person in India. FibroLAN is celebrating this year 24 years of life. It was founded in 1996 by some people that are coming from the industry. They are coming from optical transmission industry, so there is a lot of experience, a lot of knowledge. The headquarters of the company and some corporate functions are located here. Then we have subsidiaries in Central Europe and in the United States, and these are our major markets. And in the other parts of the world, we have a series of partners. In addition, we are collaborating with world-class partners on a global basis. I'm talking about high-level system integrators, global, as well as vendors, mainly of radio systems. So I will stop here to leave more time for the more interesting stuff. And Shamir, take the lead, please.
Okay. Again, good afternoon, everyone. Thank you for joining. As pre-mentioned, we will be going through a series of topics. I will try to keep things clear and focused as possible. But if you have any questions, just post them on the chat. And once we get over with the slides, we will go through those questions. I encourage you to ask questions, please, and on any related topic. Okay, so the first part of this slide deck is revolved around the evolution of the transport related to cellular networks, to the RAN. Backhaul that's the beginning, where we had base stations, even starting from 2G back in the Sonnet and SDH days. That was our backhaul network, later on to become 3G, 4G, and now 5G. And the purpose of the backhaul network is very simple. We need to connect the base stations, the radio access network, to its core, and that is typically done over these days over IP. We carry the data, all the mobile services, whether it's the voice, internet, videos, the live streaming, etc. Pretty much everything. And as we all know today, almost everything is packet-based, and in the near future, that's how it's going to be. We have management, the management plane and control planes for the base stations. And finally, and this is one of the key aspects that we will be discussing today, synchronization, to maintain proper sync between the different sites and the base stations, and allow proper operation of the network. Proper, and not just proper, but also efficient. Not having good sync between base stations would at best reduce the spectrum efficiency, and in worst cases even could even crash the network. When we talk about backhaul, the typical characteristics would be a relatively low throughput requirement from the base station. A typical LTE base station would be connected over 1 gig, Ethernet 1 gig port, and will not necessarily even consume the entire bandwidth. If we talk about that, that is even on the macro cells, macro network terms. If we look at small cells, then numbers can easily be in the range of 100, 200, 300 megabits per second. So there is plenty of room with 1 gigabit. So overall throughput requirements are not very high compared with what we'll see later on. Timing sensitivity to timing impairments is not very high. Of course, it has its limits, and I'm sure that at least some of you are aware of the 1.5 microsecond end-to-end limit that needs to be met for proper operation of the network. So it means that that's our budget. It is not easy, but compared with Fronthaul, which we will discuss later, it is still easier. Nevertheless, going through a large-scale transport network that is not timing aware is practically impossible when we want to synchronize base stations for phase. One of the key drawbacks of backhaul is the lower flexibility and scalability in order to support future services. And that is, it's not so much the backhaul network's fault, it's more the radio networks who's responsible for this. Because if we have, let's say, a small cell, 3Gs, let's even take it further to the past. If we look at a 3G small cell, the original ones were not even able to support LTE. Later on, we had 3G and LTE base stations or small cells. 5G is changing the picture more dramatically, and eventually, when we get to Fronthaul, we'll see how the whole thing can be extremely flexible and scalable, even through future generations that are still unknown or not unspecified. Looking at just a typical architecture, we have the base stations on the left-hand side with the node B, a 3G, whether it's 3G, 4G, an eNode B, or a 5G G node B. Connectivity can be different, can have different speeds, can be gigabit, can be a 2.5 or even 10 gigabit, depending on the requirements. Maybe we have multiple base stations on the site and therefore we need higher capacities, etc. Those are aggregated either in star, mesh, or ring topology, which is quite common closer to the edge of the network, of the backhaul network. And at that point, we typically move up to an IP-MPLS core. The edges of the network can also be IP-MPLS, but it is more complicated and more costly. And many operators are choosing to combine layer 2 carrier Ethernet at the edge and IP-MPLS at the core. Of course, this is a fully blown could be a fully blown large scale transport network with some serious optical links, etc. But the data technology is IP-MPLS. And that would also lead us to the EPC for LTE or the 5G core to serve the base station, as well as all the generations. We've got the controller sites, etc. From a timing perspective, we need to provide, we need to assume, and because this is true in many cases, that the IP-MPLS core is PTP unaware. That means that timing over packet will not be properly supported throughout if we only try to do that from the core. That means we need to complement the grandmasters, the PTP grandmasters located at the core with edge grandmasters. Could be one step further from the base station, or even very close to the base station, serving multiple sites on the same area, whether it's the same ring or just a close, relatively close geographical area. It's both are possible, and of course we can mix and match those architectures in order to provide also higher level of redundancy. And finally, the ultimate goal is to keep the 1.5 microsecond target for LTE and 5G phase sync required for TDD operation. At some point in the LTE era, pre-5G, there were initiatives by some vendors to promote the concept of Fronthaul. Idea is, or sometimes it was referred to as Cloud Run, C-Run. There are quite a lot of terms related to Fronthaul and the distribution of the run, or splitting of run elements. I will try to keep things simple, not to complicate it with many different terms. Simply put, what we do with what we did initially is take the base station and break it to two pieces. One of them was the radio head, which included the antenna and the analog to digital, an analog to digital converter, and sending the digital data as bitstream over a protocol commonly known as CPRI, from the site, from the antenna site towards the baseband unit. The baseband unit, in theory, was supposed to be based on commercial off-the-shelf hardware. However, this was not the case. The concept was good, the direction was correct, but it didn't pick up for several different reasons. Just as a side comment, there are a lot of similarities between CPRI or LTE fronthaul, RRH, and BBU combinations and DAS systems. The main difference is that the traditional DAS, the distributed antenna systems, were based on analog signals over the fiber as well. In this case, we're talking digital. Everything is digital, bit streams, but this is not Ethernet based. So there are some limitations. The idea, of course, is to allow us to connect different sites to distribute capacities and everything, allow us greater flexibility. However, if we look at the key characteristics, the number one killer of CPRI or fronthaul in this format was the very high throughput. If any of you who has heard or dealt with CPRI know that the bit rates are extremely high between RRH and BBU. 10 gigabit is almost nothing. If we look further down the road in terms of 5G potential, in terms of spectrum, like 100 megahertz, or even less than that, and advanced modulations and advanced features, if we want to implement that based on the same infrastructure or same functional model of based on CPRI, that would get us to easily to hundreds of gigabits per antenna. This is something we cannot live with. It's not impossible, but it is very uneconomical. We can put it this way. If we're willing to invest $300,000 per antenna, I'm sure it's possible, but I don't think anyone sensible would be doing that. And that is, again, the number one aspect or characteristic that eventually led to, or will lead to CPRI or this kind of traditional model to go away. It does exist in some cases, but it is very limited, and it never lived up to its full potential because of these reasons. We do have a very high sensitivity to timing impairments, which means that we need to connect directly the RRHs to the BBUs, and if we need to have a transport network in the middle, we are in a serious problem. We cannot use Ethernet switches and routers because this is not Ethernet, and we need to take care of timing and again the very high capacities. The idea is again to provide better flexibility and scalability, but the price is too high. Eventually, since it didn't really catch up in the market, if you choose to go that path, you are effectively locking yourself in with specific vendor. There is no real interop when it comes to CPRI, even if this is a standard interface. It is effectively not a standard. And then we get to 5G fronthaul. First of all, one of the most important and smartest decisions to evolve the previous fronthaul model was to move to Ethernet-based transport. The second smart thing was We need to have a different kind of split. We need to have a little bit more intelligence at the radios, at the radio units, while still keeping a lot of flexibility on both ends. This is where we hit the sweet spot. We have a fully distributed architecture, which allows us, again, maximum flexibility and scalability by means of connecting the different elements in a very dynamic way. It can be static, can be dynamic, but we can always reconfigure it. There is a lot of scalability and flexibility there. We can virtualize many of the functions in the network, and I will show that shortly. As I said, we're heavily based on packet transport, Ethernet, using what is known as eCPRI. So still carrying radio information or RF, not so much RF, but radio information, radio signal information, but over Ethernet packets. It is much, much more efficient bitrate wise, but it still requires quite significant throughputs compared with backhaul. There is also the notion of radio over Ethernet, ROE, but this is a lot less common, and the de facto, the predominant standard is eCPRI. Key characteristics include, as I mentioned, the medium throughput requirements. That is somewhere between backhaul and the original Fronthaul. We're still not talking about gigabit speeds. Just to get you an idea, radio units in 5G Fronthaul are starting at least for the time being, they have 10 gig interfaces, even though they're not utilizing the full throughput, possible throughput. It is very well designed for future technologies, services. Everything is a lot of elements are software defined, reconfigurable, reprogrammable, so that when 6G comes along, we will most likely be able to support at least most of it over existing infrastructure. This is, of course, highly implementation and vendor dependent, but at the end of the day, it should be very flexible. Interop, open architecture, and I will say a few words about Oran later in some of the slides. This is a key concept here and is very important for interop. One of the key sensitivities is timing. Timing is much stricter in Fronthaul, and therefore it is sensitive to timing impairments. Having a switch that is not PTP aware at the Fronthaul will not work, period. That is, it makes things much simpler. It's not going to work somewhat, it's just not going to work. And we use PTP and SyncE for synchronizing the different elements. A few words, a few terms that I just want to go through quickly. CU, centralized unit, DO, distributed unit, and RU, radio unit. The Fronthaul part is between the RU and the DU. We have the backhaul from the CU. Just imagine that you take a base station and you actually break it down to 3 pieces, CU, DU, and RU, and you can connect multiple DUs to a CU and vice versa, and same for the RUs. The mid-haul is the connection between the DU and the CU. There are all kinds of combinations like DU and RU together coexisting in the same system known as RDU, etc. One of the most important points is that DUs and CUs almost always running or operating on commercial off-the-shelf servers. Could be HP, Dell, Lenovo, Supermicro, anything. This is the dominant technology model, and that provides great flexibility and also improves the competitiveness situation, which is favorable to operators. Going through several scenarios related to 5G RAN and Fronthaul. First one, we have the radio units RUs connected to the DU, the server, and that is connected to a CU, which again in turn can be connected to other DUs as well. Fronthaul is this part, and mid-haul is between DU and the CU, and beyond that we have the standard backhaul. We do need to synchronize the DU and the RUs, and we can use a PTP grandmaster and edge grandmaster connected to the DU in order to do that. Typical rates are 10, and upstream we're talking 10 and 25 gig. The next step is to have greater flexibility and cost efficiency if we introduce a switch between the DU and the RU, a Fronthaul switch. That allows us to fan out to more radio units and still not having to have multiple NICs or too many NICs, high-speed NICs on the DU, which is limited. At the end of the day, it's a server. We can put, if we only have two or three RUs, probably the most efficient thing to do would be to put more interfaces on the server, the DU server. But if the common scenarios require more, we can have easily 8 RUs or even more than that. So we have the switch for connectivity. Of course, this has to be PTP aware switch with very high performance, and it will be connected to the grandmaster, and it will distribute the timing to both DU and RUs. There are some additional features that will be required from these switches in the future, like TSN, but I would not go into that at this stage. Finally, we can combine the grandmaster and the switch into the same system, so that we have timing being generated within the same box, and transport is also being held by the switching part of it. So this is the most integrated option of all, and probably also the most cost-efficient one. Again, we can mix and match depending on the specific scenario that we have, deployment scenario that we have in the field. There is a fair chance that we will have 2 or 3 different architectures in our arsenal. When we go to deploy the network, we will just need to fit the right tool for each case, but we don't want to standardize on 2 or 3 options. A few words about the Oran Alliance. It was established in order to create specifications that will allow interop and open interfaces between the different elements of the Fronthaul, the 5G network. This goes actually beyond Fronthaul, but we focus in this session, we focus on Fronthaul. So we have all aspects being taken care of here, and the Oran Alliance is creating specifications. It is comprised of many vendors, including already the leading ones. The idea is to have flexibility, scalability, future-proofing. Maybe most important, avoid vendor lock-in. It is recommending the use of eCPRI and functional split 7.2. I will not go into too many details about the different split options, but what we showed earlier in the previous slides was effectively this 7.2 split. And we can use either Ethernet or IP. Typically, the communication between RU and DU or the transport network would be layer 2. There is no real necessity in having a layer 3 transport in the Fronthaul. And last but not least, we use PTP and SyncE for the synchronization for the S-plane. Deep diving a little bit more into Oran-related timing, there's dedicated specification sections for that. We will go over some of the topologies proposed, which are described in LLS C1 through C4. The default tele-PTP profile recommended is 8275.1. With SyncE, 75.2 is being considered. Of course, at the end of the day, if all elements in the Fronthaul support 75.2 or even other profiles, we can always do that. It's always possible. But the Oran is recommending as the default to use 75.1. Just to give you an idea of what kind of accuracies we're looking, that highly depends on what kind of radio features we're trying to implement. But as an example, if we use MIMO, the difference, the time difference, absolute time difference on the air interface needs to be below 65 nanoseconds. This is quite challenging, and it means that on the connectivity on the Fronthaul port connected to the switch and the DU, we need to have timing that is probably better than that, or accuracies that are better than that, in order to cater for the air interface. One of the specifications, or one of the notions, is that we can use boundary clocks or transparent clocks in the transport switches. Oran specifies class B, but class B may not be enough in the not a very long future. So we need to consider also classes D, C, and D for boundary and transparent clocks. I picked two out of the four topologies. I picked two that are more relevant and combine transport and not direct connection. LLS-C1 is actually a direct connection between RUs and DUs. And we want to look at the slightly more complicated scenario, so I picked C2 and C3. On the C2 architecture, we have the timing coming from the DU over the transport network, which we see here can be based on one or more switches. And finally, timing is distributed through those switches to the RUs. This means that the switches must be either boundary clocks or transparent clocks. And again, specifications call for at least class B. The way we see it, there's a fair chance it's not going to be enough later down the road. So we must consider classes C and D. To give you an idea, I already saw one of a serious, very significant operator. Let's call it in Eastern Asia, that dictated accuracies at the frontal interface of the RUs of 10 nanoseconds. So class B will just not cut it for that purpose. Then we have the more interesting, and the way we see it today, this is probably the most, will be the predominant architecture, especially considering timing, simply because it has the best chance of serving the right levels of accuracy that we're looking at. So in this architecture, we have the transport network in the middle, generating the timing, PTP and sync E, from by having a PRTC or a grandmaster connected to the same boundary clocks and transparent clocks and distributing both to the DU and the RU. Now, it is also possible to have the switches and the grandmaster combined in the same system, which we will see shortly. Okay, so this is pretty much wraps up the more generic part. And now in the next few minutes, I will explain how we are approaching this with our systems, our products. Just a few words of introduction, not more than that. So we have two main product lines or product series or classes: the Falcon M class and the Falcon R class. The M class is targeted, is optimized for backhaul and small scale fronthaul. We have done a lot of work, interop, and trials with several radio vendors with these products, and it works very well both for backhaul and for fronthaul. And the RX is highly optimized for fronthaul. It can also be used for high capacity backhaul, but it is more geared towards the fronthaul with much higher capacities. A few details on those, or the key models. Falcon MXG. This is 1 gig and 10 gig oriented system, so it is better geared for backhaul. However, it can actually combine backhaul and fronthaul, and we've already done some experiments with that. It has an embedded, a built-in grandmaster along with the GNSS receiver. Of course, all the necessary functionality in order to support multiple slaves. Very highly accurate time stamping, 1 nanosecond accurate time stamping. So we can easily cater for very demanding requirements. It can also serve as a boundary clock, as a transparent clock, class C and D. And finally, if we have a very extreme situation regarding holdover, we can even plug in a rubidium module into this system. Its smaller brother, the Micro Falcon MXG, is targeted mostly as a grandmaster, as an edge clock. It is fully featured, again, very powerful, high accuracy, all functionality is there. And in fact, it can also do a little bit of backhaul work because it has a few, it is also based on a switch, and it has even 10 gig ports. So we can actually do a very small scale backhaul network. If we have a small building that we need to put in a few small cells, we can use this little guy here to do both the aggregation to the backhaul and to generate timing for all required elements. The new guy latest kid on the block is the Falcon RXG, and this machine has many more 10 gig and 25 gig interfaces. It is extremely powerful. It's still, again, it can do all the PTP functionality, PTP and SYNC. Accuracy is even sub-nanosecond. Built-in Stratum 3E oscillator. Rubidium is optional again on the same form factor. And another interesting point here is the support for TSN capabilities, which is expected to be required in some cases in the future. This pretty much wraps up the presentation part. So I think, Prem, we should move. We have about 10 more minutes or so. We can move, even a bit more. We can move to the questions.
Yeah, Shamir, I think there are a few questions both in chat box as well as in question and answer tab. So I would suggest you can take them one by one. I think you can see them.
Yeah, so I will start with the Q&A section.
Okay.
There's one there. The question is, how is BMCA achieved with multiple grandmasters? So I assume this refers to being a slave clock or a boundary clock. So the 1588 or PTP does define a couple of algorithms for selecting masters, and there's the BMCA, the standard BMCA. Thank you. So the question refers to Ravindra just clarified the slave clock. The slave clock, by the way, just to remind you, is usually on the base station. So this is actually an interesting point. Normally, if you do, you can follow the standard and you have BMCA and alternate BMCA, which they clearly define the methodology for selecting the right, the higher quality grandmaster. Each grandmaster advertises its quality and some other parameters, priority, etc. And it is the slave's responsibility to select. Nevertheless, we've already run into some situations where, especially using unicast, we have inode Bs that do not implement BMCA, and but we can configure multiple grandmaster addresses for them. So what we actually did, we had to tweak the grandmaster software in order and created the dedicated signaling between the grandmasters, so that we actually the effect was forcing the slave clock to switch over to the better grandmaster. This is something that we've done working with some integrators and run vendors to overcome a limitation of the inode B. I hope this answered the question. With your permission, I'll move on.
Shamir,
now we have
the next question is eCPRI is the main Fronthaul transport technology, which is expected to have very high bandwidth, quite similar to CPRI, because the IQ data is still part of this link independent of CPRI or eCPRI. Is this correct?
So basically, it is true that the data is IQ data. However, there is more processing when using eCPRI. There is more processing being done on the radio unit in order to lower the bandwidth required on the Fronthaul. This is one of the key differences between CPRI and eCPRI. So and if you recall, I mentioned the split 7.2. There are higher split as well. There is even split 8, Split 8 is getting very close to CPRI, and the bandwidth is much higher accordingly. The idea is to process more and even compress. There's also the notion of compression of the data. Usually the compression ratio can be 1 to 2, but again, this is not compared with this CPRI. The starting point is much lower than that. So in essence, yes, we still transmit the IQ data, the radio data towards the DU, but it is already going through some processing. Otherwise, it would be completely impractical, as we've seen in CPRI. Again, there's orders of magnitude difference in the throughput required.
Thank you, Shamir. There is one more question. Is SYNC mandatory along with G8275.1 for PTP?
Where is the, okay? So SYNC-E is not mandatory in most cases. However, it is recommended for two reasons. The first reason is better performance. If implemented correctly, and again, at the end of the day, there's a lot of things that are, or performance that are dependent on the actual implementation. But if implemented correctly, SYNC-E, first of all, provides much greater stability, much quicker frequency lock times, which is important when we have either a topology change or we want to switch over to another master. So SYNC-E will get us, just like in SYNC-E again, is like SDH. So we get the clock from the line very fast. Actually, SYNC-E has much better performance than SDH. And so it gives us greater stability. On top of that, SYNC-E also provides us with redundancy or some level of protection if we lose PTP. The PTP session is dropped for some reason, but we still have SYNC-E, then this is effectively holdover, and it can go like that indefinitely. If the SYNC-E source, the clock source, is not is still running, then it can go on indefinitely like that, because we have every element is clocked in a synchronized manner.
Okay, Shamir, if you go back to slide number 11, the question is FibroLAN M-class equipment is co-located with DU?
It's a good question. It is highly dependent on the deployment scenario. To give you an example, let's say that we're in an indoor environment, which means that we will have probably an IT room or a network rack or something like that, data room, could be even a data center, and the RUs will be spread around the building. So it's a question of whether we want, how is our fiber run going? We can co-locate it in the same rack as the DU, and then we have fiber runs going on to maybe different floors or different locations, and maybe it makes sense. And in other cases, maybe we'll want to have a switch in each floor, and those will be aggregated by a larger switch or by DUs at this centralized location in the building. So it's mostly a question of what is the density of the deployment, what is the fiber, how does the fiber deployment look like, etc. So it is very flexible. One point to keep in mind is that latency between RU and DU, the typical numbers are shooting for 100 microseconds. So we are limited on how long the fibers can be. The switch itself is also introducing latency, of course, and we need to take that into account. Our Falcon MX has an intrinsic latency of approximately 2 microseconds. So it doesn't take much of the budget. But if you have a switch or a router that take up, let's say, 10 or 20 microseconds of latency, that is something we need to consider in the whole scheme of the deployment.
Okay, next question. I think probably we can stay on the same slide. Which Falcon, FibroLAN product will aggregate CPRI and eCPRI from multiple 4G and 5G RRUs? Typical, there are going to be 3 numbers for each. So
yeah.
And the next question, I think in the same part is, what is the Fronthaul technology used to transport this aggregated traffic?
Okay, so when you have a combination of CPRI and eCPRI, in most cases, there are some products, very few products on the market that can actually take both CPRI and eCPRI. Because there are very few of those, they are extremely expensive. And I'm talking could be easily be 10 times higher than an equivalent model that does eCPRI only. So in order to handle that, there are elements that are attached to RRHs that can be attached, or there are some RRHs that already come this way, that convert CPRI to eCPRI, effectively making it something more similar to the 5G kind of Fronthaul. And getting these things into a packet, in which case we can handle it. The Falcon itself does not have a native CPRI interface. We have actually worked with one of the RAN vendors. It was even a few years ago, 4 or 5 years ago. We have developed a prototype of a CPRI switch. And it was working well, but we both realized, both us and the radio partner, we realized that moving forward, the data rates are going to be so high, it's going to be completely non-economical, and we dropped it. So it's possible, everything is possible, but at the end of the day, the bit rates on CPRI are just, I just like to call it insane. And to the question of the transport towards the DU, that should be packet. If you have a native CPRI connection on your switch, then then the question is very good, because you will need, the switch itself would probably need to get it over to packet as well for with eCPRI. So it can get very complicated on the switch side, and again, the bigger problem is it is extremely expensive.
Thank you. There are few more questions, Shamir. I think we still have a few minutes left,
Sure.
So we can continue. Do we support PRTC-B accuracy in Grandmaster?
Yeah, it depends. This is yes. The answer is yes. It depends on the model, and depends on the oscillator, or mostly on the specific model. It's mostly an oscillator question, because from we always use GNSS receivers that are highly tuned for timing, so they have very high accuracies. And our time stamping abilities, and the way we are able to fine tune with our front interfaces, Ethernet interfaces, and the FPGAs that we have on board, we can keep to a very high degree. Like I mentioned earlier, timestamp resolution is 1 nanosecond, so we can cater for PRTCB. And again, one of the important factors here is the oscillator. So obviously with the rubidium it's possible, but also with the no6O, not the base, not a mini 060, but higher grade 060.
Any plan for 100 gig or 400 gig timing interfaces on our product?
400 gig or, sorry?
100 gig or 400 gig timing interfaces.
Okay, this is an excellent question. So if we look at the Falcon RX, the Falcon RX has up to 825 gig interfaces, and those, although they cannot work, they cannot be bundled as 100 gig per se. But let's keep in mind that 100 gig is essentially 4 times 25. So one of the models that this is just the initial models. This is the newest family, and we do plan on having multiple models. Some of them will cater for QSFP28, so that we can have over the same fiber strand, we can have 4 times 25. And another point I would like to mention here is that as part of this family, part of our plans is to have even 10 gig PoE interfaces for indoor deployment. This is something that our requirements that is slowly coming up. And in addition to that, a smaller scale outdoor unit, like a real pole-mounted, weatherproofed unit that will have a smaller port density, but will still be able to handle all this functionality, including the Grandmaster.
I think, Shamir, there are plenty of questions, but we are running short of time, so probably we are going to take the last one.
Yeah, sure.
In 5G Fronthaul, is PTP plus SyncKey going to be the primary timing source, or it will be secondary timing source with GNSS being the primary source?
When you talk about outdoor radio units, you can use GPS for sure. If it's indoor, there's no question. It has to be only PTP and SyncKey. If it's outdoor, you can use GNSS as primary and PTP and SyncKey as secondary, or vice versa. One of the biggest problems with GNSS, assuming it's available, we can get a signal, we can get an antenna and everything, which is sometimes cost prohibitive. But GNSS is very sensitive to interferences. It's very sensitive to attacks. It is considered today, it's considered not exactly as a robust method. It is very simple, it's very cheap, it's very widely common spread, but it's easy with a $50 jammer to bring down GNSS within a 30-meter range. If you want to invest a few $100s, you can get even to a kilometer range. And that is something you can get online on the internet very, very easily. So that is one of the problems with GNSS. It is spread all over, and this used to be the main, the traditional macro network mode of synchronization. But moving forward, it is going to. We cannot rely on GNSS only. There are some high-power jammers and block entire areas of Indian 5G networks. So this is the main reason why we need to be very much more careful with GNSS. So it's possible that GNSS would actually be secondary only.
Okay, thank you. I think we have to now, finish the session because time is over. There's still a lot of questions, and we will answer those questions over email because it is difficult, to take all these questions in 10-15 minutes. So I would say thank you very much for all the participants, all the attendees who has taken time out for this session. In addition, we are going to share the link. We have recorded this session, and we will also share the slides. Do come back to us, if you have any questions or any requirements. Thank you so much. Thank you, Shamir.
Thank you. Thank you.